Hello, everybody. Welcome to another course on basics in geomathematics. I will talk about spherical radial basis functions today. They are also a very helpful tool for approximating or representing functions on the sphere. They have their own pros and cons in comparison to spherical harmonics. Again, I will tell you some basic fundamentals about them. What are they? How can you use them? And I will again give you some references where you can find out more about these functions. Let me clarify some notations in the beginning. First of all, I will only talk about the case in R3. So in R3, we have the unit sphere, which some people or many people in mathematics call the S2, the two sphere. I will call it capital omega. So it's a set of all xi in R3, which have a Euclidean norm, which is 1. As you see here, I write the Euclidean norm with a single vertical line on both sides. And I will also use Greek letters for unit vectors in R3. So I will only talk about the case in R3 on the two sphere. But it's easy to transfer that theory to the d-dimensional space. So what is a spherical, what is a spherical radial basis function? Basically, simply speaking, it's a function depending on only the Euclidean inner product of 2 points on the unit sphere. So again, since I only write single vertical lines for the Euclidean norm, the more applied version, I will also use the more applied version, namely the dot product for the dot for the dot product for the Euclidean inner product. So now, first of all, it's clear that obviously the inner product of 2 unit vectors is something in between -1 and 1. So it's a function which depends on the inner product. Now, if you talk about functions on the sphere, we have to distinguish now these 2 points. And what I'm doing here is I'm saying, okay, for example, sorry, that's not. What I'm doing here is, for example, to say that we have a point eta on which this depends, so xi is fixed in that case. You could do it vice versa, it doesn't matter. So it's a function depending on an inner product of 2 points on the unit sphere. One is a fixed point, and we consider it as a function of the other point. In that case, it's eta. That is the variable here. So why is that a radial basis function? Radial basis functions, if you know a bit more about that, if you're not in the spherical setting, if you're in the Euclidean setting, you would say a radial basis function is a function that only depends on the distance to a certain fixed point. So normally you would have something like a function, so in Rn, where you say that's a function y in Rn is mapped to f of a function of the Euclidean norm, f of norm x minus y, and x is fixed again. So how is that related to each other? And that's very simple, because if you have, again, xi and eta and omega, and if you calculate the Euclidean distance between these 2 points, I will take the distance to the square to get rid of the square root. Then this is, first of all, simply xi minus eta times xi minus eta. And from that, you get a xi times xi minus 2 xi times eta. I'm already using the symmetry because you would get xi times eta and then eta times xi plus eta times eta. Now, since xi and eta are unit vectors, their norms, so the inner product with themselves, is 1. So we get a 2 minus 2 xi times eta, which is simply 2 times 1 minus xi times eta. Which means that if you have 2 points, if you have different, if you keep psi fixed again, and you have different points eta, which have the same distance to psi, then they would also have the same inner product with psi. So in fact, functions of these properties, that they really only have that form. You have a fixed point on the unit sphere, and it's only dependent on the inner product with that fixed point. These functions have the property actually that they only depend on the distance to the point psi. So the consequence is that you get circles around psi where these functions are constant. So these functions are called spherical radial basis functions. So you don't have yet a basis, but people call it that way. And they're also called zonal functions. Okay, so much about that. Now they have some nice properties. One thing that I want to mention is if you have an integral over omega of such a function, which is a zonal function or a spherical radial basis function. So I will rewrite a lowercase omega or d lowercase omega for the surface element on the unit sphere. The gang psi is fixed, and you have such an integral over a zonal function with respect to the remaining variable eta, then two things are interesting. It doesn't depend on psi, doesn't depend on the center of this radial basis function. And the other thing is you can write it as a 1D integral, namely it's 2 pi times the integral from -1 to 1 of k of t dt. This is a very, very helpful tool on the sphere, because you will get in many cases such zonal functions, and you often have to integrate them in some reason. So you can prove a lot of things by just knowing that, or by knowing that and some other things. Okay, now it's a function depending only on the inner product. What I've already said is this inner product is obviously a something, a value between -1 and 1. So you can alternatively say, as you see it also in that integral identity, you can say, okay, it's a function of -1, 1. Now, if I assume that the k is a square integrable function, if you don't know what this is, it simply means that this integral is finite. It actually means a bit more mathematically speaking. You have to build some equivalence classes of almost every identical functions, but that's not important here. So if you know that, if you assume that's an L2 function, which is a rather weak assumption, it's not a very strong condition, then we know from some basics of approximation theory or basics on orthogonal polynomials that k can be written as a series n equals 0 to infinity, and some coefficients, I will call them lowercase kn, times the Legendre polynomials. So these are just coefficients, the kn are just some real numbers. So everything is real valued here in my case. So that's in R. And the Pn are the Legendre polynomials. Which are defined by requiring, first of all, that they are polynomials. And the first thing is that the degree of Pn should be n, so they're enumerated with their degree. The second is the integral from -1 to 1 of Pn of t, Pm of t dt is 0 if n is not m, which means that with respect to that L2 space here, they're orthogonal. And the third condition is that on the right ending of the interval, it's 1. So we can expand every k in the Legendre polynomials, every k in L2 minus 1, 1. Now, if we look a bit closer into the theory of the Legendre polynomials, which I will not do here. Again, look at the literature on that. We can say that the k in L2 minus 1, 1 can be written as a function. I will do that. I will do something that I usually warn my students of doing. So n equals 0 to infinity, and then you have a 2n plus 1 over 4 pi k hat n and Pn of t. So that's again the Legendre polynomial. This is just a coefficient here. So what is it that I'm warning usually students of? Because you don't get necessarily a pointwise convergence of that series. So it's a bit dangerous to write here t, but I think for illustrating that, making clear where the functions and where the constants are, maybe it's good to do that. But you only have it almost everywhere. You don't have it necessarily pointwise. So what is that here? The k hat n. It's 2 pi times the integral from minus 1 to 1, k of t, Pn of t. And this is what I usually call the Legendre coefficient of the function. Okay, so now what do we know? We know that our spherical radial basis function slash zonal function can be expanded into Legendre polynomials, which is a well-known system of functions. So there's a vast amount of literature on Legendre polynomials, or in general on orthogonal polynomials, or more general on special functions in mathematical physics. So you can write, you can collect a lot of identities and other properties on the Legendre polynomials, and there are nice algorithms for calculating such summations. Certainly, you would have to truncate this series here if you want to sum it up. But for such truncated series, there are efficient algorithms for calculating that. Okay, now I want to use that nevertheless as a radial basis function. So we need to get back to the sphere as a spherical radial basis function to be precise. So let me write it again. Again with the comment, be careful, it's not necessarily pointwise convergent. So I will just replace the t by an inner product of two unit vectors. So once again, to remind you, psi and eta are unit vectors. My idea is that this is fixed. Okay. So there's something else that you might need to know, or maybe already know. There are spherical harmonics that are already mentioned in the beginning. And there's also a video on spherical harmonics. If you don't know what I'm talking about here and you are interested in that specific part that I'm just now telling you, you can look at the other video. There is a so-called addition theorem for spherical harmonics, and this tells us that this 2n plus 1 over 4 pi times the Legendre polynomial, that's one side of the addition theorem, and the other side is a sum over j from minus n to n, and then you get a k hat n and the y and j of psi and the y and j of eta. So I could take the k hat n here outside, but it doesn't matter here. So the y and j, that's an orthonormal basis system of some polynomials on the sphere, on their particular cases of the so-called spherical harmonics. So let me give you the keyword. These are here, spherical harmonics. So that's another way of representing it, which you should keep in mind if you want to do mathematical theory about that, because if once you have an orthonormal function system in L2 of the unit sphere, in which you can expand this function, you can prove a lot of things. It's very helpful for deriving other identities. I will have a look now at something else. One thing is I make an assumption. I will tell you more about that in the end. The assumption is that the series n equals 0 to infinity of 2n plus 1 over 4 pi k hat n is finite, where I assume that the k hat n are all positive. If we're all non-negative integers. Why is that interesting? It helps me in one respect that I already mentioned, namely the convergence of the series above. Because with that condition, I can have a look at these summands here. Say, okay, this here I will write it as a T again. So let's use the version above. Easier. So I can estimate that now. Okay, certainly the absolute value of this is just the value again. K hat n is positive, so I can skip the absolute value here. Now, what I would need now would be the absolute value of the Legendre polynomial, but again, in the literature, there's a lot of information that you can find about the Legendre polynomials. And what you, for example, will find out if t is, as we always have it here, between -1 and 1, you can estimate the Legendre polynomial actually by 1, so by the value on the right ending of the interval. So, which means that this here is an estimate above from the summands in that series. So I'm talking about the convergence of that series here, and I'm looking at the absolute values of these summands here, which is this here, and I can estimate it by this here, which is independent of t, obviously. And this majorant, this upper bound here, is summable. It has a convergence series. So there's the Weierstrass criterion. I'm German, so I'm using the correct spelling. If you're not German speaking, you might know it with a double S here. The Weierstrass criterion says that, I will call that equation 1. Let's see if we have an equation 2 also, which tells us that this is uniformly convergent. Which has some mathematical consequences. One thing is that since it's uniformly convergent, not only that you have clarified the convergence, you can write it down pointwise, but it also implies that K is continuous. Okay. So I will have a look at a particular choice of K hat n. Let's have a look at if the K hat n is an H to the n with some H between 0 and 1. So if you do that, actually you can take something between -1 and 1, but it's, anyway, usually one would take something between 0 and 1. Then the series, if t, I will write t again, would be n equals 0 to infinity, and then I have a 2n plus 1 over 4 pi, and then an h to the n, pn of t. Why am I talking about this particular choice? Because for that particular case, we know the limit. You can find out to what this function converges. You don't have to truncate the series and just calculate an approximation to that. There is a so-called closed formula for that limit, and this is 1 over 4 pi, 1 minus h squared divided by 1 plus h squared minus 2ht to 3 over 2, and this is the so-called Abel-Poisson kernel. And this plays a very important role if you, for example, have if you have a sphere like the Earth's surface, and you want to measure the gravitational field of it or any harmonic function, then there is a so-called Dirichlet problem, which says, let's assume we know that harmonic function on the boundary, and we either want to continue it to the exterior or to the interior. In the case of the gravitational field, it would only be a harmonic and outside, so we want to extend it to the exterior. And there's a so-called Poisson formula for that, and this uses the Abel-Poisson kernel for writing down for that identity that you have there. So it plays a very important role for modeling harmonic functions in a domain with a spherical boundary. And here are some plots of these Abel-Poisson kernels for different choices of age. Now they are not plotted with respect to minus 1, 1, but they're plotted with respect to the cosine of theta, which is not unusual for representing these functions. So theta is here in between minus pi to pi, which would mean that you know that the cosine of 0 is 1, but the cosine of pi and minus pi is minus 1. So it's actually the t is ranging going from minus 1 to 1 and down from 1 to minus 1 again. So we have a maximum for theta equals 0 or for t equals 1. So and what you see is that you get kind of peaks here. So we call that a hat function if it looks like that. And you get similar structures for other spherical radial basis functions. Yeah, so you have a concentration around the 0 here. And the 0 again is theta equals 0, and cosine of 0 is t equals 1. So it's where the t equals 1, you got the concentration. But changing different values for h, you get different intensities, let's say, of concentration. So the larger h is, the thinner, the finer is the peak that you get here by looking at the functions. Now we can utilize that. It's a basic property that is which is the reason why people use these spherical radial basis functions. So let's assume we have a signal f omega. So we somehow measured something, some values, some information about f, and we're looking for an approximation to f by a function which we represent now as a j, some j equals 1 to some capital N, aj, and the kernel at eta j times xi. So I'm changing a bit my notation here. So the eta j would be the fixed point now, and xi is the variable. So we have fixed points eta 1 up to eta n here. So what does this basically mean? So you want to approximate the function by a sum of such hat functions. Now remember what we saw, the maximum, the peak of k was occurred if t equals 1. So if that what you enter here is 1. Now, when is that 1? We have two unit vectors. E to j is fixed, psi is my variable. So what does psi have to be such that we get 1? And it's obvious for unit vectors. That's the case if psi equals e to j. So it's clear that this function here is maximal if psi equals e to j. So let me write that down. K of e to j times psi as a function of psi is maximal usually for psi equals e to j. So we have n basis functions for representing our approximation, and for every basis function, we know its maximal at its particular fixed point e to j. So we have now a sphere, we have now a sphere, and we choose some points e to j here, and for each of these points, we add here some hat functions, etc. So by changing the coefficients here, I would change certainly the height of the hat function. So I could turn this here into something like that, and I could turn this into something like that here instead. Certainly, you wouldn't want an approximation which has such an oscillating form. But certainly I cannot plot that or paint that now with 100 or 1000 grid points. You have to imagine that for a large number of n, where these grid points are close enough to each other, and then you get a nice structure for representing that. Certainly, it's something that you have to balance. If you have a coarse grid of e to j points, you shouldn't take the Albert-Poisson kernel that I showed before for something like 0.95, where you have very sharp peaks, because then you would get a sharp peak around your point e to j, which goes rather almost down to 0 until you get the next e to j. So then you would really get something like that in the picture. Now, what is the advantage of doing that? The advantage is obviously that by changing these coefficients, remember what I just showed you. If your signal, for example, changes in that region here, if the signal changes in that region, you can easily adapt this by saying, okay, now I need something more because the signal has become larger, but it doesn't, which means you would have to change the coefficient to that, and so maybe also some coefficients of the neighboring radial basis functions, but changing your approximation in this area for the respective AJ would not have a significant influence to the coefficient somewhere else. So on the one hand, it helps you numerically. You can easily adapt your model, but it also is also a matter of significance, because if you use, for example, spherical harmonics are polynomial averages. So all coefficients in spherical harmonics are polynomial averages always over the whole sphere. So if you have a very small local effect, for example, a gravity change due to an earthquake or so, this is a significant change in that particular area where the event occurred, but it's globally seen, nothing very really significant. So you would have a very localized event which contributes slightly to every spherical harmonic expansion coefficient, which would mean slight contribution is something that usually contradicts the intention of getting a significant change, which is above your noise level. But if you use, for example, spherical radial basis functions, you would have in such of a local event, you would have that only a few coefficients would change, but they would notably change. It would definitely significantly change. So it's easier to evaluate such things. So that's one advantage of using spherical radial basis functions. Now, the big question is, how do I get my approximation G? And there are different ways of doing that. So how do I get G? So there are different ways. The enumeration does not mean any priorities. It's just an enumeration. One way is to say, okay, for example, if you have data of your unknown function on your signal, like f of eta j is y sub j. So you have some values on some points on the sphere. So what I usually tell my students here is, let's assume it's the temperature measured at all weather stations of the world this morning at 8 o'clock Greenwich time. So something like that. So what you can do now is you can say, let's assume these eta j are the same. So so the eta j are given by the points where you measure. And then you say, okay, let's take precisely these eta j for that. Well, maybe I can change that, which makes it a bit easier. Let's change the index, eta k is yk, so for all k from 1 to n. Because if you insert that now into that equation, so I wanted to use equation numbers, so I wanted to have an equation 2, so that's my equation 2. So in equation 2 gives you now that the sum j equals 1 to n, aj k of eta j times eta k is yk for all k equals 1 to n. So that are the conditions that you get from the ansatz for G and from the data of F that you have. So what do we know now? We know the yk, that these are the values that you measured. You certainly know your kernel. This k is also called a kernel because it depends on your points. And you know your eta j, so you can calculate this. But what you need are the aj. That's what you need to find out what your function g is. So what you have here is a system of linear equations. And if you have that, the question that always arises is do you have a regular matrix? Because only in that case, you can guarantee to have a solution and you can guarantee that this is unique. And the answer is yes. So the matrix, there's something more, namely the matrix. So obviously the matrix consists of that. So you have a matrix. Let me call it the matrix capital A. Of all these values. And you have an A, capital A, lowercase a. So the lowercase a consists of these coefficients, and correspondingly, I will have a vector y consisting of the y sub k. So, that's actually the system of linear equations that you have. For every k, you get an equation, and you get it by moving through the kth row of this matrix, so the kth row. So that's symmetry. So it doesn't matter if you have jk or kj, because of the symmetry of the inner product, it doesn't matter. So you go through the kth row, k is fixed, but j is running here, sum over aj, k, eta j, etc. And this gives you the kth value of the equation. So what you can show under the condition that I had previously, that series which had to converge and which involved the Legendre coefficients. If you have that, you can show that this matrix is not only regular, it's also positive definite, which is a nice thing to know, because for positive definite matrices in linear systems of equations, there are very efficient tools for solving these equations, so which you can utilize here. Okay, nevertheless, you should be aware of that if you have large data systems, it's still a positive definite system. By the way, it's independent of what points you have. You certainly should not have equal points, so they have to be pairwise distinct, obviously. But if you have that, you always get a positive definite matrix. Nevertheless, if you have a large data system, your matrix can be ill-conditioned. So you might have to do some regularization to stabilize the solution of the linear equation system. So this is on a well-known tool. It has a big advantage. The advantage is that you take the data points as the centers of your spherical radial basis functions. Why is that interesting? Let's go back to my example of the temperature data for weather stations this morning, 8 o'clock Greenwich time, because you do not have any kind of uniform distributions of weather stations on the Earth. So there are areas where you have every few kilometers or even less weather station, which means that you expect a high resolution of your temperature model in these areas. But there are certainly other areas, for example, parts of the oceans, where you would not have such a density of weather stations, which would mean you don't expect a high resolution. But since you put your radial basis functions there where the data are, let's assume we have here a lot of data here. Then for every grid point, you have a radial basis function. So you can add here something everywhere where this is. So which allows you to, in total, to build up a complicated structure of your approximating function, because you have a lot of degrees of freedom in this area to choose. Again, that's the advantage of having a localized basis functions like these are, because the coefficients and the basis functions concentrate on a part of the sphere. But in other areas where you don't have much data, you don't have a lot of peaks to adjust, which would anyway not make much sense. So that's an advantage of this. To give you a keyword for that, these are called spherical splines. And two people should be mentioned for that, and this is Willy Freden and Grace Wawa, who independently of each other developed these methods. Okay, there is another way, and that's, for example, if you take, you still have information, you still know the f of eta k, but you have a particular constellation of eta k, namely the eta k are a quadrature grid. Some people say cubature grid doesn't matter. It's a grid for numerical integration. So if you have an integral over some function g on the sphere, then you would know that this is somehow approximately the sum j equals 1 to capital N, some so-called weights, and then g of eta j. So there is a theory about that. There are several methods for numerical integration on the sphere. I will not go into details regarding this matter. But what you can do again, you can say now, okay, let me call it g tilde because my approximating function was g. So what I'm using here is now my function g that I had above, equation 2. Here above here. So again, my g of xi, I assumed it to be just sum equals j equals 1 to n, some coefficients aj, and then k of eta j times xi. Now, if you're aware that this is a quadrature grid, you can say, okay, somehow we're calculating an integral here somehow. Whatever this is, this integral. And you can imagine that by saying, by replacing the aj with a wj times of f of eta j. So this aj is calculated like that. So you don't solve a system of linear equations, but you just say, okay, my aj are the quadrature weights, the w sub j, times the values of the function f measured at the points e to j. Because if you do that, you would get from the above that this is approximately an integral. It in black. I want to write it in black. This is approximately the integral over omega of f of psi. Yeah, I cannot write psi. F of eta k of eta times psi d omega eta. And this is also a methodology that exists because this is giving you some filtering methods. It's a filter actually what you get here. And again, depending on the choice of your kernel, remember once again the Albert-Poisson kernels. If you take a filter like that, or if you take a filter like that here, the blue filter, the finer head function, will give you a weaker filter. It will do less filtering, but the broader filter, the black filter in the Albert-Poisson kernel, it would be the filter with a lower H. This would be a stronger filter. It would be a stronger low-pass filter. So these filters have a smoothing effect to the function f what you get in the end. So what you would do, for example, you parameterize your kernels, for example, with an H, or you can just, I will write a capital J and call J a scale. So you take different versions of kernels, and this will give you different approximations of the function f, different filtered versions of the function f on the sphere. And it's also worth looking at the differences of all these different filters, because the differences of consecutive smoothings is a smoothing and a slightly weaker or slightly stronger smoothing. Take the difference of that. These differences give you usually some interesting detail information. So you can find some localized structures hidden in the signal if you do that. And this is connected to a spherical wavelet theory. There are a lot of spherical wavelet theories. This is one way of doing it, and many people have written literature on that, and I apologize for not being complete in this respect in any way, and not being complete at all. So this the context is spherical scaling functions. So these k sub j would be the scaling functions. And what I said about looking at the differences of consecutive filtered versions, the consecutive approximations, this would be spherical wavelets. And someone who has done a lot in this respect, wavelets a bit better here. Someone who's done a lot in this respect was again Willy Free. Okay. Now there's another way of doing that. So again, we have an f of psi, and we want to approximate it by some what j equals 1 to capital N, some coefficients, and some k, which again have some parameter. So that's the third version here now. Some parameters and some eta j times psi. So another way of doing that is saying we try to get the maximum freedom of that, because what can we choose? We can choose the coefficients, for example. So the spline way would be solving the system of linear equations. The scaling function wavelet way would be use a quadrature rule for getting them. These are two ways, but anyway, you have to get the coefficients. The other point is, how do we get the eta j? In the one case, they're given by the measurements. In the other case, they're given by a quadrature rule, but nevertheless, you need to know your function on these points. And the other thing is, how do I choose my parameters? How do I choose my kernels here, the radial basis functions? How do I choose them? There is a way of optimizing that, of trying to get the best possible kernel, because what you would need in the end is, if you again have something like f of e to k is y is of k, but you can have other conditions. So for the mathematically more advanced people, you can have some linear and continuous functionals applied to f, to which you know that, for example, it's a derivative or it's an integral or something else, depending on f. So if it's a derivative, you have to take care of that the functional needs to be continuous. And what you can look at is to say, okay, let's look at what my function, so this is g of psi again, what my function psi gives me at these, okay, I should not, sorry, yeah, I'm just contradicting myself, because the point is, it's not necessarily these points. So this is, I'm leaving that, so I will have a zeta k here. So I will evaluate that now at new data point, different data points. Doesn't have to be the e to j for calculating my spherical radial basis functions. So, and I look at the difference to the data that I measured. So this is what my approximation would yield at the data. And this is what what I know, what I measured. And I look at the least square, the least square ansatz. So I sum it over k equals 1 again. Different, so the n is the number of the e to j, could have different numbers of data, capital M. So if you want to minimize that, this gives you a least square approach. But usually that's again unstable depending on the problem that you're looking at. So you can regularize it with the Tichenor-Phillips regularization by adding a term lambda times some norm of g. I will not talk about what the norm of that would be. It's a norm of the function g. So the task would be to minimize that. And by finding that, so find this. Find the coefficients, the perfect kernels, and the perfect centers of these kernels. And you can even allow that the types of scales that you're using here can be different for every summand, which again is that in fact, if you have some areas where you want a higher resolution, you can take different kernels with finer peaks. And in other areas where you have where you don't want only a coarse resolution, because the data doesn't give you more, or there's not much structure in the solution, you can adapt this again. So this is an algorithm which my research group, the Geomathematics group in Siegen, and myself have been developing for a number of years. And to give you some keywords in our FMP is actually the beginning. It's called regularized functional matching pursuit. And there is some adaptations, modifications to regularize orthogonal functional matching pursuit. And there is a more recent improvement, which Naomi Schneider and myself have done with other co-authors, which are the LRFMP and the LROFMP, and sometimes they also occur as the LIPMP. So there are different abbreviations, different versions of these algorithms. I will also tell more about this in the end, in the list of literatures that I'm now not really approaching, but I'm getting closer to that. For the more mathematically interested people, I will tell you a little bit more, because you can do the following. You can take all functions in C infinity, right, in C infinity of omega, for which you require that n equals 0 to infinity, and then k hat n to the -1 of the inner product of f, y, and j L2 omega. So it's the orthonormal basis again. It's the L2 inner product to the square that this should converge. So it's a case of n, k hat n. It's the coefficients in the radial basis functions that we had. Remember that I had a condition which requires that they're all positive. In particular, they are not 0 in that case. So which allows me to write here k hat n to the -1. If you take that, and then you can define an inner product with an index calligraphic h by saying series. Okay, sorry, I forgot the sum over j here. So you define an inner product by saying, okay, that's now k hat n to the -1, and then the Fourier coefficients with respect to the spherical harmonic spaces So it's possible to show that this converges due to the Cauchy-Schwarz inequality. So then you say h, so you take all functions f with that condition into space, you define that in a product, and h is then the completion of this space of functions, completion with respect to this inner product. And this gives you a Hilbert space. And this Hilbert space is called a Sobolev space. It might, if you know Sobolev spaces from other contexts, you might not necessarily recognize it, but they're nevertheless closely related to each other. And the interesting thing is that this Sobolev space is a so-called reproducing kernel Hilbert space. And what does it mean? It means that our kernel has a particular property, namely for every function in the Sobolev space, you can do now the following. You take the kernel at a fixed point psi dot. So this is now, I will not write as it's common. I will not write a psi dot dot, because actually the dot is the inner product that I have here. I would have to write a dot for the empty space for the variable, because it's a function that I'm entering here. But usually one doesn't write the second dot. So this is our radial basis function, and it's the inner product with f in the Sobolev space. So with that inner product that I've just defined, and then you get the function f at psi for every psi in omega. So, and besides, you have the property that k of psi dot is a function in h for every psi. Otherwise, the inner product would not make any sense. But the important property is certainly this, and that's why it's called a reproducing kernel, because it reproduces f at the point psi. So, and there's a well-known and actually established old theory on reproducing kernels that you can use for proving further properties of these functions and these methods that are behind that. So that's for the mathematically more interested people amongst you, to give you that keyword. We're talking about reproducing kernels. So it's also worth looking at the literature on this topic. So here's a very small selection of literature on these zonal functions or spherical radial basis functions. It's certainly, again, completely incomplete. And it's just a small selection. For example, as I said, Willy Freden did a lot. Here's an example of two nice books by Willy Freden and co-authors on approximation methods on the sphere. And you will also find a lot about these reproducing kernels, about the zonal functions, how you can use them as splines and wavelets on the sphere. There is another book by Fassauer and McCord on kernel-based approximation methods, where you also find something about how can you use it for MATLAB. This is not only done for the sphere, it's a general theory on such kernels, not only on the sphere. If you're more, again, with a stronger focus on the sphere, there's a PhD thesis on advances in radial and spherical basis function interpolation, where you can also read more than I could tell you in such a video. Once again, you're certainly invited to look into my literature. There were some two textbooks on approximation methods on the sphere, which are the first two in this list. And the most recent advances on this algorithm I mentioned, the RFMP or the LRFMP, you can find them in these two articles, which are on the bottom, which are the number 3, number 4 in this list. So that's it again. Thank you for listening. I hope that this could be interesting for you. I hope that you learned something about spherical and radial basis functions. Maybe you knew already a bit about that, and maybe it became some, you got some new insights into this topic. Maybe you've never heard about them. Maybe you just wanted to learn what they are. I hope I could be helpful. And once again, look into the literature. They can tell you much more about this. And I'm always welcome for constructive feedback on my videos. So thank you for staying here, and I hope that you will look at some other videos made by myself, and then we'll try to continue producing such videos. And also, maybe you want to give me some recommendations. Maybe you're interested in something particular that you want to learn more about it. I can do my best to help you answer on some other topics. So thank you very much. Bye-bye for today.